Let's talk about the limitations of our current defense mechanisms. Specifically, I want to talk about the Obtuse Decay gradient approach, and I also want to give you some ideas of what we have been doing in the past couple years on studying the physical attacks and also collaborations on attacking and defending on social media. I want to start by sharing with you a slide that I take from the DARPA GUARD program. On this slide, you can see that on the right-hand side, there is a trend of all these attack and defense mechanisms. And so you can see that back in 2014, when the first method by Goodfellow, and that is the FGSM, that was introduced in 2014, then very soon that people have introduced the adversarial training, but then people have introduced multi-stage attack like the PGD attack, and then there is a method called the distillation. Then you can go to Canini-Wagner attack, and then there is a detection again, and then more recently there's approximation attack. And so you can see that there is a back and forth game between the attacker and also the defense. And so this is really, I call it an endless game, because today you have a attack, tomorrow you have a defense, and then the year later you will have another attack, and then you have a defense. This is really an endless game. And I will give you some perspective of how to play this endless game. And indeed, I am not a big fan of this endless game, because I think that there are a lot more interesting problems than trying to defend and attack. So what I want to do is trying to convince you that the defense that we have seen so far, they look very promising. However, you got actually very easy to attack these defense mechanisms. So I want to talk about a method called the Obtuse Decay gradient approach, proposed by Atali et al. So what they show is that, as you can see from the paper title, there's a concept called the Obtuse Decay gradients, and these Obtuse Decay gradients, they are giving a false sense of security. So it was a best paper in ECE595ML 2018, and so what they have done is that they have successfully attacked 7 out of the 9 white box defenses in ECE595ML 2018, including many of the methods that I have introduced previously. The only method that can survive is the adversarial training. And so now let me talk about what is the idea behind this this gradient masking or obtuse gradient. Obtuse gradient is also called the gradient masking. Okay, and so the gradient masking means that I'm hiding away the gradients, or I am destroying the gradients, so that all these gradient-based attackers will fail. So you can think of what do I mean by hiding the gradient and destroying the gradient. You can think about the total variation denoising. What are you doing? Well, you are really trying to wash away the attacking pixels by destroying any gradient information that is present in the attack image. So in this paper, this Obtuse Decay gradient paper, what they show is that they specifically list 3 types of Obtuse Decay gradients. The first one is called a shattered gradient. It means that there is a non-existent or incorrect gradient created by the defense, like the total variation denoiser I just talked about. Another type of the Obtuse Decay gradient is called the stochastic gradient. This is introduced by the randomization schemes. The third type of Obtuse Decay gradient is the problem of vanishing gradients. This is really caused by deep neural networks, where you propagate information from one layer to another layer. The gradient will eventually vanish. So in order to attack, you just need to know that the defense mechanisms that you're using, they are introducing these problems. And so specifically what I want to do is to talk about these two types of gradients. I want to share with you that as long as you are able to recover the gradient which has been washed away, for example, by your total variation denoiser, as long as you can recover some of these gradient information back, you will be able to attack these defense mechanisms. So let me give you an illustration of what you can do when you try to attack these methods with input transform and randomization. So suppose that you have a secured classifier, which is a classifier f hat, is composed of your classifier and also your input transform. G is the input transform. Okay. Now, because G is a denoiser, we can roughly say that you want the Gx to be similar to X. Now, if you think about what is a denoiser, the denoiser is a G that applies to Gx plus some noise, and then you want it to remove all the noise and give you back the X. However, in adversarial attack, this eta is usually not very, very strong, because if it is that strong, it just becomes a hopeless problem. Okay, so normally you don't even have a very, very strong eta. Then you can approximately say that I want my G applied to X to be similar to X. This is a very hand-waving argument. It's not exact in any sense, but you can think that by just removing the noise, think that it is in a very, very small perturbation setting, then ideally we do want your denoiser to return you the clean image as much as you can. And so you can approximately say that G of X is approximately equal to X, and therefore if I want to compute the gradient, okay, because whenever you want to attack, you want to compute the gradient of your overall classifier f hat. If you want to compute the gradient of this guy, then eventually you need to compute the gradient of your G, because by chain rule you need to compute the gradient of F, and then you want to compute the gradient for your G. And so there's a chain rule involved. And so if you know G is approximately equals to X, then you can easily write that the gradient of G is approximately 1. Now, before you do this, you really need to compute this gradient of G, which is very, very hard to compute. Okay, and if you want to go backward and then you want to attack this classifier, the gradient is lost because of this input transform. And so if you want to get back the input transform, you don't even need to know what the input transform is exactly doing. What you need to do is just to approximate this input transform with this operation. So in order to attack this input transform, number one, you do not need to know what the transform is doing. You just need to know there's a transform which is doing some kind of denoising, and you replace all kinds of denoiser by this G approximately equal to X. And this is not the key. The key is the second idea. It is really to say that the gradient of G is approximately equal to 1. And therefore, when you try to compute the gradient, it's just the gradient of your classifier, which you have access to through the backpropagation. And then you can just substitute your X to that denoiser. Okay, so if this is a white box attack, you have access to the denoiser, you don't even need to compute the gradient of the denoiser, which is extremely hard to compute. So think about a deep neural network or a deterministic algorithm like total variation. How are you going to get the gradient of the total variation denoiser? That is very hard. However, by plugging in the data point into the denoiser and evaluating that result, that is very easy. Okay, and so you can now get the gradient using this very simple approximation, and then you can do the backpropagation, and then you can launch your FGSM, that type of attack, and you will be able to succeed in attacking input transforms. How about the randomization? The randomization, as I said, in any white box attack, you need to assume that you have access to something about your defense mechanism. In this case, let's assume that we know the distribution of all these input transformations. And so you have some randomness in this input transformation. However, you also know the distribution. While you do not know the specific case during your defense, you can take the average. And so what do I mean by taking the average? Well, this is your classifier applied to some kind of transformation, and then you have an expectation that is taken outside. And what you can do is that when you try to attack this entire thing, you can take you need to take the gradient of this expectation. But since expectation and gradient operation, they are somehow somewhat arguably exchangeable. So you can take the expectation outside, and inside you can take the gradient of the f. And so now once you have this, and then you have an expectation outside, then what you need to do is really to take the gradient of this guy, and then you take the average of all these gradients. And that will be enough for you to attack this randomization scheme on average. Okay, and as I said before, if you do not know the exact instance, by attacking the average case, you are just a little bit worse than you know exactly what is the current state. And so by minimizing by attacking the average case, you will still be able to attack in many situations. And this is what they have demonstrated in their paper, that even if you have a randomization, they can still successfully attack a lot of these defense mechanisms. So if you have already seen the project description in our course website, you realize that I am asking you, trying to develop a defense mechanism and also trying to explore the possibility of doing an obfuscated gradient attack. I encourage you really to take a look at this project and do your best to this project. So in the following 2 slides, I want to give you some perspective from my own personal experience working on this problem. The first comment is on physical attack. Now, we have seen a lot of very beautiful attack strategies, as well as many beautiful defense mechanisms. A very big question that we should ask is, can adversarial attack really attack systems in a real physical space? You have seen examples like these. For example, the stop sign, and also the turtle, the Google toaster. You have seen examples like these. But one thing that you may want to pay attention to is that all these attack strategies, they are done in a very controlled environment. And so if you really bring these attacks to a more uncontrolled environment, it becomes very unclear whether these attacks can still work. And so what I'm commenting here is that you can probably do adversarial attack in real physical space. However, the attack is more likely to be very strong. If it becomes very strong, then perhaps a very simple low-level image processing algorithm will be able to detect those changes. Because you think about you're really drawing the stop sign to a certain very big way. The perturbation is so strong that you realize that there's something wrong with the stop sign. You will just go ahead and pull down the stop sign. And so you also need to remember, in this physical space attack, you probably do not know the model parameters. White box attacks, they're useful to study the problem. However, in real settings, most of the attacks is black box. You do not know what the models are. And so the real challenge is in the real physical space. For example, you can have shadow, you can have perspective change, you can have angle, you can have blur, you can have noise. If you don't believe me, try to bring your camera out and then try to draw something on a pattern and then do a black box attack, and then change the lighting condition, move the camera around, if you can still attack, I'll be very, very surprised. As a matter of fact, I have never seen any real physical attack that works beyond the reported scenarios. Okay, so you can train very specifically for this stop sign, for this kind of environment, but if you change the lighting condition to something else, that will fail completely. So in my opinion, this is really my opinion, it is much more meaningful to look at the bigger problem of these issues. That is the classification in real physical space. And that has to do with what we call the transfer learning problem. That you're learning in one scenario, you want to adapt to another scenario. This is not adversarial attack. I'm not even talking about there is a hacker. Imagine that there's no hacker. You just bring your camera around and then you try to maintain your consistency of classifying objects. That is already a very challenging task in transfer learning. And I think this is a much bigger problem than trying to attack and defend. In my opinion, the only parties that cares about defend and attack will be the internet service providers, social media, or search engines, where they have a lot of content in the cyberspace. But in the actual physical space, these kind of attack seems to be not very, very common. In fact, if you think more deeper, what is the economic value of trying to paint a stop sign in order to fool an autonomous car? I just cannot imagine that why somebody will have the incentive to do so when there is really no market of doing so. Now, certainly, if you go to the search engine and social media platform, then there is a big market, because once you can put the image up, you will get the advertisement, you can get the money. But if you're talking about painting a stop sign for an autonomous car, besides going onto the newspaper, I don't see what is the economic value of doing that. Now, I also want to share with you a second piece of experience, which is that most of the attacks that you see nowadays, they are not adversarial attacks, unfortunately. Now, you will think that adversarial attack is so interesting that people should try to hack Google or Facebook or social media like these. But in fact, on social media today is not FGSN, is not PGD. What they are doing is something extremely simple. It's by trial and error that if I have a policy violating image, I will just put it onto the internet. If I got banned, never mind. I will take the same image back, and then I will draw something, I paint something, I will change something, submit it again and again, repeatedly until it goes through. And so these perturbations can be as simple as drawing a line. It can be blurring the background. It can be adding some patches. You can just change the text box, move the object from the left to the right, and so on. That is enough to fool a classifier. Now, you may say that these perturbations are very, very simple. It seems like you will be able to defend them pretty easily. The challenge is that people are really very creative because there is an economic market. Once your image is up on the social media, you get money award from the advertisement. And so people are very, very creative in terms of attacking those media. And they are very large in volume, huge in variety, and they're new every day. You just cannot imagine how creative people are when they try to put the policy violating images on the social media. And so the challenge is the scale. It's not the simplicity of the attack. It's actually the variety of attack and the unseen examples. And then they are very, very large in volume. And so you're welcome to develop any kind of adversarial training. We know that it is very robust. You can develop adversarial training, try to defend against these attacks. I can promise that nothing will work from my experience. Really? Why? Well, because although these attacks are simple, they are rich. You have a lot of these different types of attacks. Therefore, in social media today, if you ever have a chance to go to these places to do an internship, you will realize that they have a large team of human content reviewers to catch these policy violating images. This is an open problem. This is a significant open problem. This is a good open problem to work on. It's not just about adversarial attack. It's about repeated content policy violation attacks. And so we have some work on doing that. And if you're interested, we'll be very happy to talk. And so let me summarize this lecture by giving you some take-home messages. I want to first comment on that this Obtuse Decay gradient paper is pretty much concluded that the adversarial training is the only method that can withstand their attack when the paper was published in 2018. And so all the methods that we have talked about so far, especially the pre-processing and also the randomization, have been defeated by this Obtuse Decay gradient. So if you want to propose something new, you really need to withstand their attack. Adversarial attack is still very hot today. And I know also aware of there are many works trying to do, maybe we can prune the network parameters so that you can gain robustness, or you can, because you have a big neural network and so it's overfeeded to the noise, and therefore if I prune the network parameters, I may be able to gain some robustness and stuff along this line. But to me, this is just another form of regularization. Okay. In my personal view, I think that adversarial attack is largely an academic toy problem. This is really from a very personal experience working on these physical attacks and also trying to work with people in the social media platforms and trying to understand what the outside people are actually attacking. It seems like the adversarial attack problem is a very interesting academic problem, but it seems to be a disconnect from the outside world. And so in my lab, we have been working on several problems. Specifically, we're working on problems like low light, very low light classification and recognition through random media. And so you have an imaging device, and then you are seeing objects that are very far away, so that would be distorted in many ways. And so can we do some kind of transfer learning, and so that you can learn in one scenario, and then you can transfer your learning strategy to a different scenario. And these are really good open problems, because if you can solve that, you will significantly improve the recognition ability in harsh environments. Okay, so I want to stop at here, and when we come back in the next lecture, we are going to talk about one more theoretical subject, which is the trade-off between robustness and also the accuracy. So I will see you next time on the internet.